This is the like purple egg white powder, but whatever the most popular water it's similar purple. Yeah, I'm like that was dropping.
Hi everyone. Galaxies, this is my favorite topic. I work in galaxies. I'm an extragalactic astronomer, so I study these. And so we'll talk about what we typically think of as the largest things. One thing, otherwise you think of them as groups of galaxies and clusters, but these are sort of like one coherent thing. We'll talk about the Great Debate, colors, shapes, and we'll talk about what active galactic, mergers and active galaxies on Thursday. So, when photography was invented, these are some of the very first photographs, sort of like at the end of the 19th century. So you can sort of see like these are all stars of our own Milky Way, and then you've got this fuzzy smear there. This is the Andromeda galaxy, so one of the very first pictures taken, and so it was very unclear whether or not these things belonged to our Milky Way or not. So they were called nebulae. This is a later picture in color, so that you can now do with a digital camera. But the whole debate was, do these things belong to our Milky Way or not? Are they part of our Milky Way? Are they just glowing gas? Or are they similar to our Milky Way, but really stupendously far away? So that became a debate, and in sort of early science kind of style, this was going to get settled by having two prominent people essentially pile up the evidence against and do a debate in person. And so that feels very, so this is my one exception on the dead white guy rule, because this feels personality bound, right? So if you do a discussion like this, if you hear certain people talk about it, like it sounded like this was sort of like a wrestling match, and it became personality bound. And so whether or not these things were island universes, their own universes far, far away, or part of our own Milky Way. And so the term island universe, I just want to highlight that came from Immanuel Kant. So Kant you might know from your philosophy class, but this was one of the first things that was one of his contributions, which was like, look, these things could be their own islands of stars far, far away. And I think I really like the term island universes, and sometimes we still use that as a sort of poetic term for galaxies. And so the conflict peaked with the Great Debate. One side was Harlow Shapley, the other one was Herbert Curtis. And so Herbert Curtis said that he was on the side of the island universes, they're separate galaxies, and Harlow Shapley said they are part of our own Milky Way. This wasn't immediately resolved, and it doesn't help that I think Herbert Curtis wasn't a great public speaker, and Harlow Shapley was, right? So you're now going by force of personality, and the problem was both of them had reasonable arguments, and now, for example, one of Shapley's arguments was that there was this observer, and he mentioned that this pinwheel galaxy was rotating, and if I can see the rotation in real time, then this can be millions of light years away, because then it would be so big that the rotation would mean that the stars in this galaxy would rotate faster than the speed of light. So if I can see it rotating, it has to be in our Milky Way, it has to be closer. But this was literally the visual observations by this Adrian von Manen guy, and it was, as you look through a telescope, and if you look through a telescope, if you look through binoculars, if you look through anything where you have to squint, things look a little bit like they rotate. You could totally convince yourself that something's rotating, or convince yourself that you saw something move. So this is hearsay. This is not reproducible experiments, right? This is going, I trust this guy as an observer, and therefore he said that he saw it rotate, therefore it's true. No, I would like to see data. So the resolution of the Great Debate really could only be solved if if we got accurate distances to those spiral nebulae, to these fuzzy little things. And so how can we measure distances in astronomy? With parallax, standard candles, luminosities, or A and B? 1, 2, and 3. Yes, luminosities alone won't do it. We need an absolute luminosity then as well, right? We need to know how intrinsically bright it is. So standard candles and parallax works. Now, one of those was variable stars. Right at the beginning, we worked on variable stars, and like this is one of the nearest Cepheids. You can actually see where it's shed some of its outer layers. But here's the plots from the Harvard computers, the name for the women who were plotting this data, and were transcribing the data from photographic plates, estimating their brightness, and so it becomes brighter and goes back down, and that sawtooth diagram, that gives you a standard candle, that gets you a standard brightness. And so the brighter Cepheids had longer periods, that gets you the Cepheids, type 1 Cepheid variables, period in days, luminosity, gets us a distance. So what was the other standard candle again? O stars, supernova, black holes, or M dwarfs. Can anybody remember what the other standard candle was? Starting in 1, 2, and 3. Majority B, supernova is the other. And so because the stars in the Magellanic Cloud are roughly the same distance, this was an intrinsic relation between pulsation and luminosity. We can use that, but that was only the Magellanic Clouds. You can sort of go, okay, fine, the Magellanic Clouds are a separate little, island of our archipelago, so to speak, right? We've got the Milky Way and then the Magellanic Clouds, but everything else is part of the Milky Way. So I'd have to find Cepheids in other galaxies, and that's what Hubble did. And so he found first Cepheids in Andromeda, and then found Cepheids in several other galaxies. And that sort of settled that great debate. The great debate was right at the beginning of the 20th century. It's about 100 years old. So only for about 100 years have we realized that all those little fuzzy things, they're distant galaxies, our universe is quite vast. And so that whole external galaxy, external to the Milky Way, ended the great debate with better data. I think this is a quintessential difference if you look just to how scientific controversies get settled versus how you can imagine doing a political or any kind of other settlement, right? If you have to convince a bunch of people, you can put two great orators on a stage and basically have them pile up arguments, but also use every trick up their sleeves to convince you, right? This is what you do in debate class. But if I'm trying to convince the scientific community, they're all just going to go, where's the data? Can you show me a direct link to? I can only settle a thing if I go out and get more data. So usually scientific inquiries or scientific controversies end when we get a bunch of extra data. And that's the first thing we'll end up doing. So this is most famously now known as Hubble's law. We also named the Hubble Space Telescope after him. That is that the distance from the Cepheid variables and the redshift that you observe, the movement of that galaxy, are related. So just to reiterate, redshift is the observed wavelength minus the rest frame wavelength, the one that we get in the lab, over the rest frame wavelength, the lab one. That is the velocity that is going over the speed of light. And so if you have spectra, you see those emission line or absorption features move. If something's redshifted, it's moving away from us, right? So Edward Hubble's car, object in the mirror are bluer than they appear. They are coming towards me now. And so between the redshift, so that's that ratio, and then the distances, you can actually see a relation between those two. So what is it called when an object is moving towards us? Redshift, blue shift, it never happens. 1, 2, 3, and I made it option B so that I see redshift, I see blue shift, both all red voting cards. So this is what Hubble found. This is his original plot, figure 1, distance, velocity distance relations among extragalactic nebulae, right? So we still kept calling them nebulae because that's what people call them originally, and only later were they called galaxies. And the distance and velocity seem to be related, so that is interesting, that all the galaxies near us seem to be going away. We'll talk about that next week as well, what the implications are, but one of them is that there is a constant ratio between the distance and that velocity. You can measure that. We did that in 1929, so we're coming up on the centenary of that. And so outside of the Milky Way, we got that these were all the components, and we now know that all these galaxies are external. So there's a lot of extra stuff. The dark matter, we didn't know about that at the time, but everything else implied strongly that suddenly our universe was a lot bigger, and there was a lot more stuff in it, and it was expanding, right? Everything was moving away from us. So, for galaxies, we're trying to do the following things, right? We're trying to understand the observational properties of galaxies in the nearby universe. We'll discuss the variation in morphology, colors, and later we'll talk about active galaxies, like what that means if they have a black hole. So the Milky Way sort of looks like this. So as soon as you start getting pictures of like Hubble pictures with the Hubble Space Telescope, this is the lecture that I say the word Hubble a lot because it's also the name of the telescope, the law, and the person that found the original classification. So switching between all those. And so this is sort of what it looks like outside, on the outside, right? It's got arms, it's got this central bulging bit, that's more yellow, the arms seem to be a little more blue, and then you have this brown stuff in between, that's the dust, that's the interstellar matter. And so as you get more clear pictures of, and color pictures of galaxies, again, this is probably the part where I should dim the lights slightly because I got a whole series of nice pictures of galaxies. Most of them from the Hubble Space Telescope. It uses the same wavelengths mostly as we do as humans. I get this a little darker here. Yeah, there we go. So you start seeing like individual differences. You start seeing that, you know, they have these blue sets of big bright stars, so you can sort of almost see the individual blue stars. These are bright, then you see a couple of really bright things, and they go like, yeah, those are from our own Milky Way, right? So if you see something that has a cross like that, those are called diffraction spikes. That only happens if it's really bright and fairly close. Everything else, you see sort of even more distant galaxies. You definitely see one there. Behind it, right? So it's all, everything sort of along the line of sight. A friend of mine calls this windshield science, right? You look at it and it's basically anything that's squashed onto your windshield during the trip. So this is our Milky Way, that's stupendously far away, and this is the nearby galaxy. So in the local galactic group, we really only have the Milky Way and Andromeda, and those are the two big ones. And everything else that we sort of locally see, they're all called dwarfs. They're all fairly small. You sort of got the Large Magellanic Cloud, Small Magellanic Cloud, and then everything else is just about smaller. Triangular Galaxy is the only mid-sized thing nearby. So if we want to study anything bigger, we're either looking at the Andromeda Galaxy, because it's the nearest example to us, or we're looking quite a bit further away. And so this is sort of a local retinue of galaxies. So if we're studying the local volume, the local galaxies, then it's mostly dwarfs. So that's a good thing to remember, that every time you see these nice big spiral galaxies, they're usually the heaviest in a whole posse of smaller stuff that you often miss because it's fainter. But if you look locally, it's like, yeah, it's two heavy hitters, one mid-sized, and everything else is sort of illy-piddly. And so the small and large Magellanic Cloud are the closest neighbors, and you can sort of see that they are. So if you are in the southern hemisphere, you'll see something that looks like a cloud. This is why they're called clouds, because at night they look like sort of an individual cloud that's lit up from below, but it's not moving, right? It's windy. You see every other cloud move, but these things don't, with the wind at least. So these are sort of what you see visually from the large and the Small Magellanic Cloud. They look odd. They don't have that spiral structure. There's just bits all over the place. This is just a faint, fuzzy thing, the Small Magellanic Cloud. And so we call those irregular galaxies because they don't have a particular shape. Spiral galaxies have the spiral shape. Elliptical galaxies look like an ellipse, but these are irregular. They don't have a good shape. So the Andromeda Galaxy is another spiral, has these spiral structures in it, spiral arms, and then the central ball. So that seems to be a twin to our own Milky Way. And here's a neat part. This is the biggest picture Hubble ever took. And so this is the size of the moon on the sky, and so it's several moons in size. So this is the whole picture. And if you're wondering why it has this odd shape, it is 667 separate images with Hubble all stitched together. So each block here is sort of a 16 by 6, 8 by 16 shot, and it's really like Hubble looks at a tiny bit of the sky, and so I remember having a discussion going like, oh yeah, this would be great to do an Andromeda, but nobody's going to be crazy enough to have us do almost 1,000 hours of time on with Hubble on Andromeda, and then somebody actually did, which was quite cool. So we can actually see the details of all the stars and in there. So if we take that picture, sorry, flipped it around, because I'm looking at like a little patch here. And then this is what you see with Hubble. You see it's completely filled with both bright red, bright blue, and a whole bunch of yellowish stars. Well, that looks familiar. That looks like the polar magnitude diagram, right? So they're both spiral galaxies. It's not immediately obvious because the Andromeda Galaxy is fairly inclined, and we're in the middle of the Milky Way, so it's really hard to see what the shape of the Milky Way is. But if you then look at other galaxies, again, I have plenty. These are really fun to take pictures of. If you have a small telescope with a digital camera, for example, it'll take you a while. Like it takes several hours to take a picture. This is another, you start seeing that spiral structure very clearly. And some have loose spiral arms, some have two big spiral arms, some of them have loads of them. So there's a lot of personality in these spiral galaxies. So if you work on them, for example, you almost immediately go like, oh yeah, that's that one. Oh yeah, that's like, oh, this is M101, right? I know the phone numbers because I've worked on them long enough. And they all have enough distinguishing characteristics that you sort of pick up what it is immediately. The Whirlpool Galaxy, kind of obvious why it's called that. We're looking straight down on it, has these big spiral arms, and is a favorite here in the Northern Hemisphere. If sometimes you just sort of wonder what happened, so this one looks like something happened here, and so if you look at it more closely, you realize that some of the stars are rotating the other way, so this probably had a collision, and more on collisions on Thursday. And so every time you look at these, you realize that, yeah, the blue blobs, that's where we have young stars, right? That's where we have lots of bright O stars, and we know that they don't live very long. So if we see blue bright stars, they must have just formed, because if we wait any longer in cosmic terms, like 20 million years, they're gone. So they must have come up pretty recently. So the spiral structure, the spiral arms of galaxies is where new stars are being made, because we see the most short-lived ones still there. So this is lots of O and B stars, the ones that live very briefly, and then not so many of those, no new stars being made right in the center, but all through the disk. This is the site where gas is being converted into new stars. So in a very shorthand, spiral galaxies is where the universe makes new stars. Turns these are star forges. They turn gas into stars. Like I said, I have a million of these. I love showing the pictures. They're pretty. Each of them has personality. You can pick out how many spiral arms you'd like, figuring out how many there are. This is called part of the winding problem. If you start with a disk, and so you can imagine, I don't know how many of you eat yogurts with fruit in them or something, but if you have, like, start stirring it, it becomes this little spiral pattern, but 2 stirs in and everything's pink, right? Well, this is the problem with this spiral structures as well. If we start with a spiral structure like that and it winds two, then it should smooth out, but it doesn't. And so what we think is happening is that this is sort of a traffic jam of stars. They sort of, stars come in, sort of bunch together, and then leave. So the pattern of the spiral structure goes at a different speed as the stars go around. That make any sense to you? Okay, great. So this is sort of like the traffic holdup, but it also means that there's a little extra stuff there, and that's why you get new stars there as well. This is triangulum. So it is a spiral disk. It has spiral structure, and so even intermediate mass galaxies have that spiral structure everywhere, and it's very fascinating to study the star formation in our nearest neighbors. Some of them are a little lopsided looking, so maybe they got dinged by something nearby or sloshing around. We don't quite know, but they all have these. Some of them are really symmetric, some of them are really not, and so why that is another study, right? So this is M81. And I keep using the word M because that's the Messier catalog. He was a fellow who was in the 17th century, was looking for comets and got really annoyed that there were all these little fuzzy things. And so he made a list of like not comets, don't bother with them. And he's now known for the Messier list. And so we still use that for galaxies. This is a lovely spiral with lots of symmetry. And if you see them edge on, this is what they look like. So this is NCC 891. I think in a previous version of this class, I basically said with every picture, this is my favorite, probably, but this is one of the ones that I studied with my collaborators. And you can see that the dust is a thin streak throughout, and then with some little tendrils going off on either side. So it's a very thin disk with a little bit of thickening in the center. So considering how wide these things are, they're very flat. So whatever you make, if you want to try to make galaxies in a computer and also understand how they work, you have to end up with something that is just pretty flat. But yes?
So is this picture and the one on the previous slide like actual pictures?
This is a Hubble picture. This is a Hubble Subaru plus Hubble picture.
So how do we?
Yes.
Like, so how far away is this?
This is about 12 megaparsecs away. So we can do this, these kind of pictures for stuff that depends a little bit on your telescope, and with Euclid we're going to do more. But about to 20 megaparsecs you can see a lot of detail. It gets fuzzier and fuzzier as we go out, but I'm showing you the ones that, so you can see the most detail. These are the nearby galaxies.
How do we see beside and
We don't, this is two different galaxies.
Oh,
Right.
okay. I was
Yeah.
like, how is that possible?
Yes. No, you're hitting on something fundamental, right? I'm assuming that this guy and this guy are sort of the same, but I'm getting only this profile shot for this one, and I'm getting this inclined, shot on that one, and I'm getting a full-on view on another. And I just showed you that they have quite a bit of variance, right? There's ones with 2 arms, there's ones with 8 arms. There's probably similar physics at work, but also each one of them seems to be a little unique. And so what we're seeing right now is the result of 10 billion years of evolution. So all that history, all the stars are sort of in there. And so I work on the appearances of galaxies, and so yes, it has all the information in there. Boo, it has all the information in there. And I only get one angle. And that one angle is really the trick, because hey, is it every galaxy the dust so thinly distributed? I can only tell if I'm looking right edge on them. But only those are the ones where I can study that. But if I'm looking at this one, for example, I have to assume that that's the case. All right, so this is the problem for astronomy. We're an observational science. I can go, hey galaxy, can you give me like a side shot? I would like to check you out from that angle. Can't do that. Sorry, we're just getting that one, so I have to get clever about that. The nice thing is we have many examples, right? So this is another fairly nearby one, and so if you can see that if there's lots of star formation happening, you can see sometimes the gas leave the disk. So there's like violent processes as well. So trying to synthesize this comes with two different tricks. One of them, can I explain all the different shapes that I'm seeing, and also the further back I look, the older the picture is. So if I look at more and more distant galaxies, and this is what we're doing with James Webb, when did spiral arms like this start? When did a bar like this start? And so when do we start seeing these guys? So looking what they like, see if galaxies change the further I look backwards in time. Because the further I look, the longer it took the light to get there, so I'm getting an earlier and earlier picture. And so with James Webb, we can look about 13 billion years back, so I'm getting a really nice long baseline there, but I'm looking back at toddler pictures of one generation, middle school, then high school pictures of different galaxies, and now I'm looking at middle-aged galaxies. So what changes and which ones do I see more of and less of? Now this is the other main kind of galaxies that we see, elliptical galaxies, and you can see there's also a bunch of them nearby. They're yellow, they're really smooth looking, and it's really hard to tell them apart. I know people who study these things for a living, and they would have to squint every time and basically tell which one it is based on the stars nearby or something, because they all look like a smooth blob. And so why do we have, roughly speaking, spirals that we can tell apart really, really well, that have blue stars that are forming, and these yellow blobish, maybe with a little bit of dust sprinkled on top, but no blue stars, no new stars. And then we have irregulars like the Magellanic Cloud. So why is that, right? So the blue color indicates a presence of massive stars. Oh, I learned British English as a kid, so I keep typing color with OU. I'm sorry about that. I try to be good about it. I do, and I don't notice it every time. So those are massive stars. So if young stars means recent star formation, right? So if we see these, the blue bright ones, those are easiest found. We also have these, I'm sure, but only if we have recent star formation, then you see those. Because if it was a little later, then they have moved off to they died off really quickly. So a galaxy that appears to be populated by mostly red stars, never had blue stars in the galaxy, had blue stars that are not present anymore, but were a long time ago, have been around long enough for the blue stars to have already evolved into red stars, never contained enough gas to have blue stars to develop, has blue stars that are being blocked by dust. Rephrase that a little bit, yeah. Volume 1, volume 2, volume 3. Got B and I got C. So, you know what that means? Turn to your neighbor, even if the two of you agree, and convince them why your answer is right. You got 90 seconds on my laptop. Volume 1, Volume 2, Volume 3. It's fun to watch. Got like opinion here, opinion there, move. Okay, I've got B and C. It has blue stars that are not present anymore, but were a long time ago, and has been around long enough for the blue stars to already evolve into red stars. So the blue stars were there, and they evolved to red stars, and both of them are B and C. I find sort of the same phrasing. This is a friend's, like I said, I need to rephrase that into one. but it is important to they have either evolved into red stars, more likely, they have exploded. The big ones explode, remember, they go into supernova, they go into, they become white dwarfs, black holes, neutron stars. So B's the best one here. They were a long time ago. They've disappeared completely. They've gone away. The red stars are more of the intermediate masses. So the red stars that you still see, like they evolve maybe quickly here and then die off, right? So this is, they don't stay here. If you're a massive star, an intermediate mass star, you don't stay here at the giants for very long. But if you see a lot of red stars and it's long, long ago, that's all these. So it's lots of idly-piddly small stars. So elliptical galaxies contain very few massive stars. They have their star formation ended a long time ago. That's also why they look so smooth. They're a little further away maybe, but they're smoothed out because it's all little stars. There are no big stars sprinkled in there, not even big yellow or red stars. Right, so that tells us that star formation ended. These things are called red and dead. Yes, it says red and dead. Red and dead meaning that, yeah, they died ages ago. As in, we think of this galaxy as alive if it's still making new stars. And if it stopped doing that, this is just chugging along with the stars it still has. So something switched it off, and we'll talk about that something also on Thursday.
Could we have a couple?
Oh, yeah. Try to make, oh, excellent.
We got it.
Try to make enough of them.
Sure.
Anybody need one still? Go for it, make a group. It's this one, isn't it? Yeah. Sorry, we don't have a color photocopier, so all your group works are always black and white. And especially with something like this, I really feel sad about that. But this is the same picture as it is on there, I think. Yes. done? Almost? Okay. Just another minute. That's funny. I only ran out once in my career, and after that, I just make too many. Apropos to nothing, but I got started in undergrad working on this little blob here. So this is a very special galaxy for me. I know this one the longest. A few years ago, we got time on the Hubble Space Telescope to look around this M01. So it's funny how you have like really long relationships with these things. So you keep going back to the same galaxies. Somebody should do a sociological study in that. I wanted to emphasize like the blue galaxy, the blue stars are the youngest part of the galaxy, but if you then look at a smoother yellowish bit, that means it's smaller stars, because if I put a whole bunch of small lights together, they blend together quicker. And so these are the older, still main sequence, but older and older stars. And so that's what they have in common with these ellipticals. These ellipticals are all completely comprised of like these G-types, like our own sun, or even smaller stars that live for 10 billion years and longer. And so even if you get a Hubble picture like that, right? The Hubble sees the most detail, and if you look at the background, this is a deep, deep image. We see all these fun little background galaxies. You can really pick them out, and then you've got the smooth fella right here, and that's it. It stays very, very smooth. And if you're trying to look very careful, then some of them seem to have a little bit of a disk, but no blue stars. So that's a bit of a mystery, right? So why are they like that? And so these are called lenticular galaxies. Some of them look sort of like they still have a bit of spiral structure left. Or they look like this again in the Hubble picture. So an edge on, so again from the side. Each of one of them are different galaxies, right? Every time I show you a picture, it's a different galaxy, because we're trying to get a picture of what they look from different angles. And so perfectly edge on, yeah, there's definitely a dusty disk still there. Maybe a little bit of blue light there, but most of it is smooth and red and dead. The Sombrero galaxy, I don't know, I don't see a sombrero in here at all, but apparently the first person who took a picture of that was like, oh, that looks like that hat, because it does have that ring here and a bit of a brim, and then the rest of it's all smooth, ball of yellow stars. So the Sombrero galaxy is the nearest example of an elliptical galaxy that we have, so this is the part where we can actually take apart the stars with Hubble. Others are too far away. You see these faint streaks sometimes, and so sometimes they're elliptical, they're yellow, but they have a little bit of dust left in the streaks. So Hubble did two things at the beginning of the 20th century. He figured out that these nebulae were moving away from us. That was, I would say, enough contribution already, but he was doing the thing that you do if you don't know what things are, which is how many of every kind do I have? So suppose you're Darwin and you land on the Galapagos Islands. What is the first thing you do? You sort of figure out, I have these kind of birds. There's this many of a yellow beak, this many with a red beak, there's this many. So you start to sort them into categories. Maybe the categories will tell you something. Maybe not, but maybe I'll see a pattern later. But you first have to do the stamp collecting. This isn't science per se. It is more of a, wow, there's a lot of different stuff out there. How do I make sense of it? So you classify, you make classes. And so he had classes with spiral galaxies with a B, so a bar. So there is a elongated structure in the center, and spiral galaxies without. There's ones with a small bulge, and there's ones with a really big bulge. So SA is a big bulge, SC is a small bulge. So as we go along these two parts of the tuning fork, we get smaller and smaller bulges, more and more disk. S0 are those lenticulars, the ones that have a tiny bit of disk left, and everything else is ellipticals. And really, we go from E0, what looks like a circle, to E7, which looks like a cigar, or like, well, one of those cartoonish Zeppelin kind of cigars, right? So that's what we've got. And then on the side, we have a big trash bin that says irregulars, doesn't fit our classification at all. And so this often is a thing that happens, right? You start classifying, you're like, oh, I have this system. And this is usually the system that gets taught. And then also, by the way, there's everything that doesn't fit my system. It's important to remember that people, when they're trying to make sense of things, often end up with a miscellaneous bin that they can't make sense of, and before you know it, it's 10 or 15 or 20% of your population. So really, does your system really work? We still talk in galaxies in these terms, but irregulars is an incredibly important component. They're just small and often faint, so we didn't pick up as many of them. These are all the big bright ones, so those are the ones you can see far, far away. So we're a little skewed, we're a little biased in that direction. If we're looking at an elliptical galaxy, and yes, I took the correct football here, we are talking basically about American or rugby football, and it depends a little bit on the angle. So this is purely, the classification is purely viewing angle. If I'm looking at it, along the line, what is it, the axis here, the throwing axis, then that is an E0. If I'm looking at it on the side, it looks like an E7. That classification tells me nothing except for my camera angle, right? It doesn't tell me intrinsically how elongated the thing is, just that I'm looking at it either this way or sideways. With the spirals, the classification tells me something about how prominent the disk is and how prominent the bulge is. Like, that's an intrinsic property. So I want you to note that these are intrinsic properties. That's viewing angle. That doesn't tell me anything intrinsically of like what the galaxy looks like. It just tells me which angle I'm looking at it on. If they are all sort of E5 shaped, they're all football shaped, and it really completely depends on whether or not I'm seeing them like this or like that. I should bring a football. So that doesn't tell me anything. So that comes back to your question, like, it's viewing angle sometimes. Of course, Hubble didn't know that. He was just in the process of figuring out that these things weren't even in our Milky Way. So he neatly classified everything into E0 to E7, but really they're all the same rough shape. They have similar masses, so what causes these to look so completely different? They look different. One of them is still actively forming stars, the other aren't, and the answer to that is hinted at in another population of even rarer galaxies. So if we see something rare, that means it either doesn't happen very often, or if it happens fast. So if I see something transition from spirals to ellipticals, or from ellipticals to spirals, but I never catch it, that means it either never happens, or it happens really quickly, because blink, you missed it. So you can have things transition from A to B, like you can imagine, caterpillars to butterflies. When do you know that those are actually the same animal? Only when you actually catch them doing that transition. When you carefully watch and you go like, wait a minute, that caterpillar is up to something, and then suddenly 3 weeks later it's a butterfly, right? You have to pay attention, but also notice that all the caterpillars have disappeared, and the butterflies have popped up, right? So if you see something like that happen, then like if you see sort of like all the caterpillars disappearing, all the butterflies, you can go, well, maybe all the butterflies ate all the caterpillars. In a sense, they did. If maybe I'll just rarely see one conclusion. Oh, maybe that's the transition point, right? So interacting galaxies, when I see two of them close together like this, what is happening? Well, this is still very much a spiral, M51. This is a beautiful thing to take pictures of from your backyard. It still works even in Louisville. And so the colors of galaxies tells us something. Like, this thing is still forming stars. That thing is not, right? It's elliptical. This is the nearest example of two galaxies close together in what is basically a gravitational interaction. And so this thing is forming tides on this spiral galaxy, and we think that part of the reason that you see these very clear arms is because it sort of just got a nudge from the tides from this other companion, this slightly smaller companion. That one is not forming stars. This one is forming stars as fast as it can because it just got tidally rocked, basically. So what do the colors of galaxies tell us? They tell us what kind of stars are where. Blue means recent star formation. Red means there's no recent star formation. Dust shows up as dark or brown streaks. Discs and football, US, not Europe. And so, that was it already. And so that's what we can learn. And on Thursday, I want to talk about these, and that's what we can actually use the planetary a little bit more. Because we're interested in seeing that interaction. We already showed you this when we were doing tidal interactions, right? When we have these two spirals, we actually know that Milky Way and Andromeda are going to hit each other. And so when that happens, they transform into an elliptical, just to give you a preview. And so if we see interacting galaxies, maybe that's the way we go from spiral galaxies, disky galaxies, to ellipticals. Because one of the problems is, if you're in a neatly rotating disk, that's nice and stable. So why would you change your orbit? Orbit angles cost a lot of energy, so you need something else to whack you out of your orbit. And so that is what you see in ellipticals. There the stars go every which way, and so something must have really realigned these galaxies' guts, basically. So you need something the size of another galaxy to do that. And then they shut off star formation. So they run out of gas, or they almost run out of gas, and then they don't make new stars. And there's a reason for that, and that's sitting in the center. So those are the reasons that so galaxies transform. So what I study is not just the formation of galaxies, how do you get a spiral galaxy like that, but also how they transform, how they evolve over time. Do those bars, for example, stick around? Now, we found them with Hubble, already 7 billion years ago, so galaxies have bars, so they could be 7 billion years old, but the percentage of galaxies that have bars is much lower. So disk galaxies seem to be forming bars and then keeping them. But then we saw a galaxy that even older, almost 10 billion years ago, with a bar already. So bars happen early. Spirals happen early. But also, we see the occasional elliptical pop up early. Not a lot, but just a few, and we see their number increase over time, and the number of disks sort of stay the same or decrease, which tells us that something is eating the spirals and turning them into ellipticals. So that gives us a direction. And then if you look how dense everything is, in denser environments, we see more ellipticals. So if you see lots of galaxies close together, we get more ellipticals. That means if they interact a lot, if they bash into each other, then we get more ellipticals. These are all the hints that you can get from just observing. Because again, we can't run the time forwards. We don't see these things move at all. This is the picture that you saw. So this is one of the first galaxies that a sketch in the photographs sketch was made of. So you see the sketch of the Earl of Ross. If you permit me, I love talking about the Earl of Ross because this is how crazy English gentry is. He owned a good chunk of Ireland, as you do, and he really liked astronomy, as you do as a gentleman in the 19th century. So he decided to make the biggest telescope, of course, on his estate. It wouldn't do to travel to somewhere else. So he made a really big telescope in Ireland, known for its good weather and clear nights. So he has this, and it's called the Leviathan. It's literally standing between two giant walls, and it's sort of hoisted into place. And so that's when he looked down and took a picture of M51. And so he took a sketch, and it looks quite like this. So it's kind of neat to see that, yes, we're still looking at the same thing. Nothing has moved in this. Nothing will move in our lifetime. Yes, everything rotates, but it takes millions of years or billions of years for actually the morphology to change. So they're really far away. They're sort of the equivalent to our own Milky Way. There's a lot of different kinds of spiral galaxies. They all are forming stars in the outer disk. The ellipticals don't, so we need to somehow kill star formation in order to get from and reshape it from a pancake to like a muffin, basically, or well, no, to a football. Yeah, so go from a pancake to a really, really bad pancake. I don't know, English muffin, something like that. And so in order to get to ellipticals, and so we'll talk about that, how that happens on Thursday. Yes? All right, grand. See you all on Thursday. Any questions? And I'll happily answer them. Are you missing something? Put every slide to check. Okay, good. The trouble is, we find wallets from like a semester ago. So